Welcome to our presentation of our measurement of an ECG signal that we took from a database. This is for signal processing, and the group members are Ebba, Jonas, and Mobina.
We have chosen to work with an ECG signal, an electrocardiogram. But what is an ECG signal and how does it look like? An ECG, as mentioned earlier, electrocardiogram, is the process of producing an electrogram of voltage per time of the heart's electrical activity. This is done by placing electrodes on the chest of an individual to record the heart's electrical signal. In other words, a way to measure a person's heart activity. In medical field, this signal is used to detect abnormalities by comparing it to an ideal signal. Image 1 shows how an ideal signal looks like. A full period of an ideal heartbeat consists of the P wave, the QRS complex, and the T wave. But let us discuss them one by one. The P wave represents atrial depolarization. The QRS complex represents repolarization of the atrial and depolarization of the ventricles. And lastly, the T wave represents the repolarization of the ventricles. We choose to collect our, it was the previous slide. Yes, we choose to collect our data from a database, and we chose 1% out of 90 individuals and chose 5 different recordings at different times from that person's heart recordings. Each recording is 20 seconds long and has a sampling frequency of 500 Hz. The recording method that was used is called lead ECG, single lead ECG method. And the raw data that we collected from this database, the raw signal that we collected from the database included some noise that we are hoping, or our aim is to remove them or reduce them. And it includes 3 types of signals, which are called baseline drift, equipment interference, and EMG noise, which is a high frequency noise. As mentioned earlier, the sampling frequency of our signal is 500 Hz. 500 sampling frequencies are suitable, for it allows us to catch the quick changes during the period of heartbeat, and we need to be able to catch the electrical changes to identify our signal. Between 200 to 500 Hz is generally considered the optimal for both time and frequency domain. Any lower frequency or any higher would not be acceptable and would not show the basically good results. The signal that we chose was originally in time domain, which means that the signal is based on amplitude over time. Image 1 shows the signal, which is in time domain. By using MATLAB, we converted the original signal, which was in time domain, to a frequency domain, which is represented by image 2. By looking at these original signals, we can see that both time and frequency domain has high and low frequency noises. And in order to remove these noises, we designed some filters that would reduce or eliminate them. During this step, namely the filtering out some noises, we face some challenges. Removing the 50 Hz noise was one of the challenges. This 50 Hz noise is known as power line noise. Power line noise or instrument noise is a common occurrence in almost every sort of signal, and there are many different solutions to this error. And another challenge was baseline drift. which is what makes the signal wander up and down the amplitude axis, taking the form of the wave. This is caused by muscle interference or movement. So if the patient basically but a human breathes. So by breathing, this noise is caused by breathing, and sadly we cannot make the patient hold their breath for 20 seconds. So this noise is usually removed by filter. When we were planning our project, we came up the following questions as our research questions: reducing as much as noise as possible. Yes, sorry for that. When we were planning our project, we came up with the following questions as our research questions. The first one was to reduce as much as possible, reducing as much noise as possible without removing too much of the vital parts of the signal. And what type of filters are the most effective? Which filter is cheapest or most expensive? And what types of filter is optimal type for real life usage? And lastly, how can we filter our signal so that we can compare it to an ideal heartbeat? Right. So it was during this last question that we noticed that we would never be able to achieve the last research question, or like be able to answer to this question, because it is not possible for a human to have an ideal heartbeat or an ideal heart signal that we represented in the first slide. We realized also that reducing as much as noise as possible without removing too much of the vital parts of the signal was a bit of a challenge. So we changed our research questions to the following: reducing as much as noise possible without removing too much of the vital parts of the signal, effectiveness of the different types of filters and their characterization in MATLAB, and lastly, how can we compare a MATLAB system to an ECG physical machine?
So when sampling all of these ECG signals, we have two different parts. The most common used one, and especially in like healthcare, is the 12-lead ECG. That is consisted of putting 10 different electrodes on the person's chest, on their arms, and on their legs. These electrodes are like sticky plates that you just push on the skin, and they are gonna transmit and watch the signal and correct them in a electrocardiogram, representing the electrical activity of the heart's different parts, and mostly atrium and ventricles, like Mobina told in the first slide, how the wave is consistent of. It's why it's called the 12-lead ECG. However, in our sampling, we took this from a database, so we did not choose the sampling method ourselves. However, the measurements can come out with using lead eye, which means that you put on the arms, left hand, and compare them to each other. You also have it on the leg to have like a grounding situation. Because of this, it's easy to measure. You don't have to have as many electrodes, and it's not as easy to put them wrong, so you get like no signal in the end. However, when you don't have as many signals to compare because of the many types of electrodes, it's gonna be much more noise, and by smaller or like huge error situations when you are able to compare them as much. However, in the recordings that needed for this particular project, the signal was supposed to be noisy, which is why we thought of using these measurements anyway because of the noisy signal. And also this method is not as affected as 12-lead ECG where we put them. So if you have it longer up the underarm or more to the wrist, it doesn't really matter because it will find the heartbeat anyways. And with the proper filtering of the ECG signal with only using 3 electrodes total, it's easy to find all the different intervals and segments from start to top anyways. And when filtering this signal, we used 3 different filters, or 2 filters that are the same, a stop band filter and 1 high pass filter. All of these filters are Butterworth based, which means that they are steeper and is easier to use in this kind of sampling and signal processing. Iris is EIL filters are better in this work, and generally, since it often work faster and require no phase information. So to compare it, to use a FEAR filter that are better when you have a linear phase response. So when you don't have a linear curve, it's better to use an IR filter. And the Butterworth is it has no ripples in the stop band, and it's made to monotonically decrease frequency response in the transition region. We also use the high pass to take away the low frequency noise that is supposed to make, like we can see in the next slide, just a bit quick, that it's making it very difficult to see all the different parts of it. It looks like you have taken a big Sharpie and done away with it. So the high pass is to take away all the take away all the lower frequencies on the smaller wave. Stop band filter is to take away all the higher frequencies instead. That makes it also very stoppy. And the stop band filter that we have that is between 59 and 52 hertz is mostly or only because the 50 hertz noise. We had a lot of trouble removing it, and we didn't get it to be filtered out with just using 2 types of filter, which is most commonly used. You just use like a high pass and a low pass to get away with that 50 hertz noise. We needed a specifically stop band filter to just remove it. That's why it's so adjusted to just around that 50 hertz noise. And it's not required all the time, but in our project, we needed a filter for basically just removing 50 hertz noise. Up in the right corner, you can see the 4th, 3rd, 2nd, and 1st order of Butterworth filter. We have in all of these used 4th order filters just because it's steeper and makes a better response. We get a clearer signal in the end after using these filters, and this is why we used just the 4th order.
The result that we got is, as you can see in the following pictures, in time domain, we got a much better clear view of what we are working with, and we can much easier decipher the different segments and intervals that Mobina talked about in the beginning that we wanted to be able to map out. As Ebba said, the baseline drift, we use the high pass filter to remove. That is one of the most common use for it. We also used a smoothing, a certain amount of smoothing for the time domain as well, which was achieved by the following code that you can see right under baseline drift, which is we took a certain amount, here we used 15, to smooth out every value so that the graph doesn't seem as choppy again. So you can see you have the 2 images in time domain where we zoomed in on a 2-second span, where you can see the first image, the one above, where it's much more chalky and up and down, and it's a bit harder to get the information from it. And in the second picture, we have smoothed it out, so it's much easier to read the information that we need. And in the frequency domain below, you can see what we started with and what we ended up with. And once again, as already been mentioned, we used bandstops filter to work our way to figure out and to remove the unwanted frequency and noise. So what we ended up with is a good representation of an ECG. It's not perfect, but we're pretty happy with it. Sampling and working with several signals worked fine, and we did end up using different signals and different measurements to test that it is somewhat reliable in that it can work with almost any signal that we put in, or at least from the database that we used. And the problems we had during this project is mostly that MATLAB is a huge program. There's so many different ways to do these kinds of stuff. Doing filters, building functions, plotting functions, and everything from small things that you think, we will solve it in just a minute, to bigger, larger endeavors that will take weeks to complete or to figure out or to just understand, so you know what we're doing. Also, as we see here, is it better in real life or digital? Of course, the working on the computer, it's much easier to just set a certain amount of numbers and type it in, and the computer will handle it. So in real life, we will have a lot more variation in our equipment and the patient that we're working with and everything. So the variety there is much more larger than anything we can recreate in our program. So will this work? Probably. It is a good representation, but it's and as I said, we had our struggles with the MATLAB and coming up with how we should go about our project and how we are supposed to reach our goal. But in the end, it worked out. We, as you can see in our smooth time domain image and in our frequency domain, we removed all the unwanted frequency we wanted to remove. We got our functioning ECG signal, and we're happy with what we got.